Good day, G10. Welcome again to our second lesson for the third quarter. So, for today, we will be dealing with factoring polynomial functions. And our goal for these topics are factoring polynomials and proving the remainder and factor theorem as well as the rational root theorem. As we start, let us take this problem. The volume of an ice cream cone is 100.48 cubic units. If its height is 2 units more than its radius, what are the dimensions of the cone? The main point of this lesson is to answer this question. How do factoring polynomials facilitate finding solutions in real-life problems and in decision-making? This lesson has two parts. The first one is proving and applying the remainder and factor theorem. The second one is factoring polynomials. Starting with the remainder and factor theorem, we have. So let's start with the remainder and factor theorem. Recall that in the division algorithm, when a polynomial p of x is divided by a polynomial d of x of degree less than or equal to the degree of the dividend, there exist unique polynomials q of x, the quotient, and r of x, the remainder, such that p of x is equal to d of x times q of x plus r of x. Considering this, we will prove the remainder theorem. It states that if the polynomial p of x is divided by x minus c, the remainder r is a constant and is equal to p of c, or simply, p of c is equal to r. And here is the proof of the remainder theorem. Considering the division algorithm, when the dividend p of x is divided by x minus c, we can write it as follows. P of x is equal to d of x times q of x plus r of x. Substituting x minus c to the divisor, we will come up with p of x is equal to x minus c times q of x plus r of x. Since x minus c is of degree 1, r of x must be a constant. Thus, r of x is equal to r. Evaluating p of x at c, we have p of c is equal to c minus c times q of c plus r. And then p of c will now be equal to 0 times q of c plus r. By simplifying, we will come up that p of c is equal to r. For example, find the remainder when the polynomial p of x equals x cubed plus 5x minus 7 is divided by x minus 2. There are two ways to find the remainder when p of x is divided by x minus c. That is the first one, using synthetic division, or calculating p of c by substituting c in the given polynomial function, or simply the remainder theorem. First, starting with the synthetic division, we have 2 as the value of c, while the numerical coefficient of the dividend are 1, 0, 5, and negative 7. And the synthetic division goes like this. Giving us the quotient x squared plus 2x plus 9, and the remainder is 11. The second method, using the remainder theorem, we have p of x is equal to x cubed plus 5x minus 7. Substituting 2 for the value of c, we have p of 2 is equal to 2 cubed plus 5 times 2 minus 7. Further simplifying, we have p of 2 is equal to 8 plus 10 minus 7, which will give us p of 2 equals 11. Therefore, when the polynomial p of x equals x cubed plus 5x minus 7 is divided by x minus 2, the remainder is 11. Let us have another application of the remainder theorem. The expression x cubed minus kx squared plus 5x plus 3 leaves a remainder of negative 11 when divided by x minus 2. Find the value of k. To solve for this problem, we have to let p of x equals x cubed minus kx squared plus 5x plus 3 and r is equal to negative 11. Using the remainder theorem, we have p of 2 is equal to negative 11. Substituting 2 for c, we have 2 cubed minus k times 2 squared plus 5 times 2 plus 3 is equal to negative 11. Simplifying, we will come up with 8 minus 4k plus 10 plus 3 is equal to negative 11. Isolating the variable k at the left side, we will have negative 4k is equal to negative 11 minus 8 minus 10 minus 3. Simplifying the right side of the equation, we will have negative 4k is equal to negative 32. Dividing both sides by negative 4, k will be equal to 8. To check if our answer is correct, we will be using the remainder theorem. The obtained polynomial is p of x is equal to x cubed minus 8x squared plus 5x plus 3. Evaluating the polynomial at x equals 2, we will have p of 2 is equal to negative 11. And by substitution, we will have 2 cubed minus 8 times 2 squared plus 5 times 2 plus 3 is equal to negative 11. The left side of the equation will become 8 minus 4 times 8 plus 10 plus 3. And by further simplifying, that will give us negative 11. So therefore, the left side and the right side of the equation are equal, meaning to say, the value of k is really 8. Okay, so that's it for the remainder theorem. Moving on, we now have the factor theorem. It states that a polynomial p of x has a factor of x minus c if and only if p of c is equal to 0. Proving the factor theorem, we will consider the division algorithm when the divisor is of the form x minus c. That is, p of x is equal to d of x times q of x plus r of x. And if x minus c is a factor of p of x, we have p of x is equal to the quantity of x minus c times q of x plus 0. And evaluating the given polynomial at c, we will come up with p of c is equal to c minus c times q of c plus 0. But c minus c is equal to 0, so therefore, p of c is equal to 0 times q of c plus 0. And we will have p of c is equal to 0. To further understand the factor theorem, let us have this problem. Determine whether x minus 4 is a factor of x cubed minus 2x squared minus 11x plus 12. Take note that x minus 4 will only be a factor of the given polynomial if and only if p of 4 is equal to 0. Starting with p of x equals x cubed minus 2x squared minus 11x plus 1, and substituting 4 to x, we have p of 4 is equal to 4 cubed minus 2 times 4 squared minus 11 times 4 plus 1. And simplifying, we will have p of 4 is equal to 64 minus 32 minus 44 plus 12. And we have p of 4 equals 0. Further checking our answer, we can use synthetic division. The value of c is equal to 4, and the numerical coefficients of the dividend are 1, negative 2, negative 11, and 12. And the synthetic division goes like this. And the remainder is equal to 0. So since p of 4 is equal to 0, we can now say that x minus 4 is a factor of x cubed minus 2x squared minus 11x plus 12. Another application of the factor theorem. Find k so that x plus 3 is a factor of 2x cubed plus kx squared minus 8x plus 3. Solving for k, we have to let p of x be equal to 2x cubed plus kx squared minus 8x plus 3 and p of negative 3 equals 0. Starting with p of negative 3 equals 0, we will substitute negative 3 for all the variable x on the given polynomial. We will have 2 times negative 3 cubed plus k times negative 3 squared minus 8 times negative 3 plus 3 equals 0. Simplifying the left side of the equation, we have negative 54 plus 9k plus 24 plus 3 equals 0. Isolating k on the left side, we will have 9k is equal to 54 minus 24 minus 3. Thus, 9k is equal to 27. And dividing both sides by 9, we have k is equal to 3. Checking our answer, we have to evaluate the obtained polynomial 2x cubed plus 3x squared minus 8x plus 3 at x is equal to negative 3. Since x plus 3 is a factor of the given polynomial, we will have p of negative 3 equals 0. And then we will have 2 times negative 3 cubed plus 3 times negative 3 squared minus 8 times negative 3 plus 3 equals 0. Simplifying, we will have negative 54 plus 27 plus 24 plus 3 equals 0. And we will come up that 0 is equal to 0. So meaning to say, k is really equal to positive 3. Moving on the second part of our discussion, we will have factoring polynomial functions. In this part, we will discuss the rational and integral root theorem, the fundamental theory of algebra, and the Decart Rule of sign. Let us start with the idea of the roots or zeros of a polynomial. A root or zero of a function is a number that, when substituted for a variable, makes the function equal to 0. Thus, the roots of a polynomial p of x are values of x such that p of x is equal to 0. Take note that the roots of the polynomial is the value that makes the function equal to 0. Recall that when p of x is divided by x minus c, and it results to 0 remainder, therefore, x minus c is a factor. This idea leads to the concept that we can identify the roots of the polynomial by identifying its factors or vice versa. For example, determine whether x equals 2 is a root of p of x equals x raised to 5 minus 4x cubed minus 2x squared plus 8. To solve for this, we will evaluate the given function at x equals 2. Starting with p of x equals x raised to 5 minus 4x cubed minus 2x squared plus 8, we will substitute 2 to x, giving us p of 2 is equal to 2 raised to 5 minus 4 times 2 cubed minus 2 times 2 squared plus 8. P of 2 is equal to 32 minus 4 times 8 minus 2 times 4 plus 8, which will give us p of 2 equals 32 minus 32 minus 8 plus 8. Therefore, p of 2 is equal to 0. And since p of 2 equals 0, we may say that 2 is a root of p of x equals x raised to 5 minus 4x squared minus 2x squared plus 8. Next, the fundamental theory of algebra. If p of x is a polynomial of degree n and with real coefficients, then it has at most n real roots. If a root or zero occurs in m times, it is called a root or zero of multiplicity m. For example, how many roots does the given polynomials have? The first one, f of x is equal to x cubed minus 2x squared minus 4x plus 8. It has at most 3 roots because the degree of the polynomial is 3. Since the factored form of the given polynomial is f of x is equal to the quantity of x plus 2 times the quantity of x minus 2 squared, it has 2 actual roots. Specifically, we have negative 2 of multiplicity 1 and 2 of multiplicity 2. The exponents of each factors will give us the idea of the multiplicity of each roots. The second polynomial, we have g of x is equal to the quantity of x minus 4 times the quantity of x plus 3 squared times the quantity of x minus 1 cubed. It has at most 6 roots because the degree of the polynomial is 6. Third key point is the Decart Rule of sign. It has 2 parts. The first one is the positive real roots. The number of positive real roots of the polynomial p of x is either equal to the number of variations in sign in p of x or is less than that number by a positive even integer. The second is for the negative real roots. The number of negative real zeros of the polynomial p of x is either equal to the number of variations in sign in p of negative x or is less than that number by a positive even integer. For example, how many possible positive and negative roots does f of x is equal to x cubed minus 2x squared minus 4x plus 8 have? For the positive real zeros, we will deal with the change in sign of each terms on f of x is equal to x cubed minus 2x squared minus 4x plus 8. We have the terms of the given polynomial starting with positive x cubed, followed by negative 2x squared, followed by another negative term, negative 4x, followed by the last term, positive 8. In this case, we have 2 variations of sign. For the negative real roots, we have f of negative x equals negative x cubed minus 2 times negative x squared minus 4 times negative x plus 8. Further simplifying, we will have f of negative x equals negative x cubed minus 2x squared plus 4x plus 8. And here, we have only one variation of sign. The possible positive and negative roots of the given function are 2 positive roots and 1 negative root. Since these 2 already sum up to 3, which reflects the degree of the polynomial, there will be no imaginary root for the given function. Since there are 2 possible positive roots, we can still come up with another combination of the nature of the roots of the given function. Take note that the number of positive real zeros of p of x is either equal to the number of variations in sign in p of x, in this case is 2, or is less than that number by a positive even integer, meaning to say, we can still subtract 2 from the existing 2 for the possible positive roots, giving us 0. Therefore, we may either have 2 positive root or 0 positive root. But for the negative roots, we will still have exactly 1 negative root. So therefore, if we will have 0 positive root and 1 negative root, we may have 2 imaginary roots. Therefore, these are the 2 possible combinations of the nature of roots of the given polynomial. We can only determine which of these 2 combinations will be true once we have solved the actual roots of the given polynomial. At this point, we will be discussing the rational root theorem and the integral root theorem. These two theorems will lead us to solving the real roots or the actual roots of the given polynomial function. The rational root theorem states that suppose that the polynomial function f of x equals a sub n times x raised to n plus a sub n minus 1 times x raised to n minus 1 plus a sub n minus 2 times x raised to n minus 2 plus up to a sub 0 has integer coefficients and p over q is a rational 0 in lowest term, then p is a factor of a sub 0 or the constant term, and q is a factor of a sub n or the leading coefficient. While for the integral root theorem, suppose that the polynomial function f of x equals x raised to n plus a sub n minus 1 times x raised to n minus 1 plus a sub n minus 2 times x raised to n minus 2 plus up to a sub 1x plus a sub 0 has leading coefficient 1 and integral coefficients, then each rational 0 of f of x is an integer that must be a factor of a sub 0 or the constant term. For example, taking the given polynomial in the previous example, we have f of x is equal to x cubed minus 2x squared minus 4x plus 8. Determine its rational zeros. For step 1, we have to use the Decart Rule of sign. Take note that there are two possible combinations for the roots of the given function as indicated in the previous example. We will be solving for the real roots of the polynomial to know which of those will satisfy the given. In step number 2, we have to determine the possible roots using either the rational root or the integral root theorem. Since the given polynomial function has a leading coefficient of 1, we will be using the integral root theorem. And here, the possible integral roots are the factors of the constant term, which is 8, which are positive negative 1, positive negative 2, positive negative 4, and positive negative 8. So therefore, we have 8 possible integral roots for the given function. For step number 3, we have to test the possible roots using synthetic division, then factor if possible. Using the synthetic division, let us test if positive 1 is a root of the given function. If c is equal to 1 and the numerical coefficients of the given function are 1, negative 2, negative 4, and 8, we have the synthetic division process as shown below. Since the remainder is 3, 1 is not a root of the given function. Therefore, let us choose another one. Let us take 2 as the value of c. And again, using the synthetic division and having the numerical coefficient of the function 1, negative 2, negative 4, and 8, we have the solution given. Since the remainder is 0, 2 is a root of the given function. After obtaining the first root of the function, which is 2, we obtain the quotient, which is x squared minus 4, and this is the so-called depressed equation. The depressed equation is already in second degree, so therefore, we can factor or we can take the factor of the given function. Thus, we have the quantity of x plus 2 times the quantity of x minus 2 equals 0, equating both factors to 0. To solve for the values of x or the roots of the function, we have x equals 2 and x equals negative 2. So upon factoring the depressed equation, another roots are obtained, which are 2 and negative 2. That's the idea of the remainder in factor theorem and factoring polynomials. Hoping you've learned a lot, G10, for this lesson. Thanks and God bless. See you in our synchronous session.